All right. Thanks so much for the invitation to speak here, and thank you all very much for being here. I hope you enjoy this talk. So I'm going to tell you about, in order to tell you about the hastened atom spectral sequence or supercohomology, well, I got to tell you about what supercohomology is. I got to tell you about what hastened atom spectral sequences are. And it would also be good for me to say, why on earth are we doing this thing? So I'm going to do all of those things. But first, I wanted to mention a couple things. Here's a picture of this spectral sequence I'll say a little bit more about in a moment. And also, this project is joint work with Wei-Chung Ye and Matt Yu. So I want to make sure to mention that. So here's this picture. I need to write a couple more words. This is the computation of the supercohomology of BZ2 to the K. And then there's a twist using the hastened atom spectral sequence. So here, K is 3. I don't know what word it thinks computation is. I apologize for that. So K is 3. This is E2 equals E3 equals all the way up to EK. And this is EK plus 1 all the way to E infinity. So the thing I want to draw your attention to more so than anything else is, I mean, okay, it's a nice picture, but if you're familiar with these kinds of atoms computations, if you've tried to do a like an atoms computation of say the KO homology of BZ2K or KU or whatever, usually it's there's a mess of differentials and then there's a mess of extension problems on E infinity. And the reason I picked this example is not only was this an example we wanted for the applications we had in mind, but it's nice. Okay, there's still differentials, but there's a theorem that computes them all. And then on E infinity, the super cohomology groups themselves are determined completely algebraically. So we really thought this example would be harder. So I wanted to show you because I thought it was cool. But without further ado, what are we actually going to do? I better tell you what supercohomology is, as I mentioned, and why does it deserve this name? This is a pretty grandiose name. So supercohomology, no surprise, is a generalized cohomology theory. And then why are people interested outside of homotopy theory? I'm going to tell you about how people previously computed this before our work that, to be clear, work to appear, but that we're finishing up. So what did people do before this? And what motivated us to go in and really do something new? I'll say something about the general formalism of hastened atom spectral sequences, which is due to, I believe it's Behrens, Hill, Hopkins, Mahowald, and then Brunner and Rognus in their TMF book wrote up a really nice general account. And then putting it all together. And maybe I'll even say a word about the proof. Here are some possible takeaways from this talk. And there's different things for, things different people might find interesting, different subsets of the audience. So why are people outside of homotopy theory interested in this? It's always nice to have that. Another potential takeaway is what is a hastened atom spectral sequence? Oops. I apologize for my handwriting. If at any point anything is hard to read, please let me know and I'll rewrite it. Um, comparing and contrasting different methods of computation. So we've got the atoms spectral sequence as usual, the Atiyah-Hirzebruch spectral sequence, and the hastened atom spectral sequence. You know, did I write too many S's? I did. I'm sorry. And I'm going to be focusing mostly on KO and KU modules for reasons that will become apparent. So, what are the relative strengths and weaknesses? This was something which was not our initial goal. Our initial goal was to solve this problem of getting better at computing supercohomology. But it turns out it tells you something interesting about the well-trodden story of the atom spectral sequence for KO modules. And so, I think that would be a cool takeaway, or at least it was a cool takeaway for me. What are some tractable, so open, interesting, and tractable computations with this hastened atom spectral sequence that the three of us have been working with. They're useful in mathematical physics. So it's, I got into this whole business because I think these computations are a lot of fun. I think given that this is the electronic computational homotopy theory seminar, I imagine many of you feel similarly. So a nice takeaway is like, what are some other computations that would be good and or fun and or not too hard and or not too easy to do? And so just as a spoiler, computations of this form tend to be twisted supercohomology of the classifying space of a finite group, where G is a small two group meaning P group, not N group, such as the dihedral group or the quaternion group of order 8. So these are things where, some stuff is known, but no one's done the computations. It'd be cool to have them. Okay.
Hey, Arun, could I ask a question? You
Of
just drew
course.
mine, so that sounds like a perfect time to ask that. In number four, when you talk about tractable computations, what do you have in mind? Do you have in mind things that people do by hand, or do you
Oh,
have
yes.
things that are done by machine?
So
Or
everything
maybe
in
both.
this is done by hand. So I would so my get the thing that we've been seeing consistently is that computations of so a twist of supercohomology lifts to a twist of connective KO, and the atom spectral sequence for that twist of connective KO is approximately as difficult as the corresponding twist of supercohomology. So, for example, for the dihedral quaternion groups, it should be possible to do everything by hand, but not easy. Did that address your question?
Yep.
Okay, cool. Are there any more questions while we're here? Like, please ask the question if you want. I just want to get this written down. So let me say what supercohomology is. Supercohomology is like, I remember before I took multivariable calculus, I was like, wow, this looks super intense. There's all these triple integrals, and there's like these weird curly D signs, and there's like these upside down deltas. And I was like, this is going to be some crazy stuff. And like, that's not wrong, but I remember how I felt when I learned that a triple integral is just an integral of an integral of an integral. And it wasn't as hard as I've been hyping it up. Supercohomology is kind of like that. It's a big name for a generalized cohomology theory that's not that crazy. And I'll say something about why it deserves to be called supercohomology in a moment. So it's the generalized cohomology theory associated to the spectrum. So I'm going to call it SH. The reason being that we typically denote homology with a right side up H, so we can denote cohomology with an upside down H. So, and then S for supercohomology. So what's going on here? So first, S is the sphere spectrum. We take the Postnikov truncation. 2 degrees less than equal to 2. So we just keep the Z, Z2, Z2. And then over here, this is something that people like to call the Brown-Kamenitz dual. Except if you look at Brown and Kamenitz's original paper, they use Q mod Z, and I want to put C star in place of Q mod Z. This changes approximately nothing, but I do want to be honest. So the effect of this is to say that SHN of X is equal to Homs from this Postnikov truncation of the sphere homology into C star. So if your spectrum is finite type, Q mod Z, C star, not that much changes. So as an example, what is the supercohomology of a point? Well, we've got a C star in degree 0. We've got Z mod 2 in degrees 1 and 2, and we've got 0 otherwise. So this is a nice, this is a nice spectrum to have. I do want to give you one warning. Is this? Yeah, that's a nice bright color. Some references call. So we kept 3 homotopy groups this year, 0, 1, 2. Some references will take only 2 homotopy groups and call that supercohomology. So, and the history is first physicists discovered this supercohomology theory, the Talos wrinkled 1 theory, and called it that. And then they were like, actually, well, we actually need the Talos wrinkled 2 one, the one that's appearing in this talk, when we do the computation. So because of that historical accident, there's this confusion. So just be careful in the literature. So why the name? So let's consider the Morita 2 category of algebras over the complex numbers. So objects are algebras. Maybe I'm supposed to say finite dimensional here. Morphisms are bimodules, and 2 morphisms are bimodule homomorphisms. So I can take the invertible things, and that is a group like E infinity space. And so it corresponds to some connective spectrum. So it's loops infinity of a connective spectrum. And indeed, that spectrum is, after a shift, its ordinary C star valued cohomology. So we just get ordinary cohomology. And the proof is pretty straightforward. You say, what are the homotopy groups of this? You discover there's only one. It's degree 2, and it's C star. That tells you you have an Eilenberg plane space spectrum. Now let's make the story graded. So we take the Morita 2 category of Z2 graded algebras with the grading, so that the symmetry structure implements the graded commutative tensor product. So now we've got a group like infinity space. What is the corresponding spectrum? Now I need to be careful with shifts, but I believe it's this supercohomology spectrum. This is the theorem of Dan Fried in his Vienna notes on string theory. So in physics, people tend to call these things superalgebras. And because they show up, they're the things that lead to, when people talk about supersymmetry, this is the algebraic structure behind that. And then this terminology has, osmosed its way into the math literature because honestly, it's cool. And so these things are off. This is the Morita category of superalgebras or the super Morita category. So the cohomology theory that you get from it deserves to be called supercohomology. Um, and that's the reason for the name. The next thing I want to do is I want to talk about twists. So
I'm going to dare to ask another question, if I may.
awesome.
So when you define SH, I mean, clearly what you're doing is you're taking, HZ and then you're adding in eta and eta squared. I mean, that's
Yes.
the true concretion. So how does adding eta and eta squared correspond to going from just the Morita two cat, from the ungraded C algebras to the Z mod 2 graded C algebras? Like why is it eta and eta squared that somehow measure the difference?
So the reason is, what is our new data? So at the zero category, the object level, sorry. Well, what are the Z2 graded C star algebras that are invertible? Well, there's Cliff 0, which is C. And now there's an object called Cliff 1, which is C, and then E1 mod E1 squared is, I painted myself into a corner, somewhat literally. So Cliff 1, normally I would need the generators to anti-commute with each other, but we've just got 1, and then E is odd. So the group of isomorphism classes of invertibles under tensor product is Z mod 2. And because we took the Brown-Kamenetz dual, this is actually eta squared. And then 1 morphisms. So pi 1 is it's ought of the unit. And so what is a Z2 graded bimodule over C? Well, it's a Z2 graded vector space. And if it's invertible, well, then we've got Z2 again, which is C with even grading and C with odd grading. So again, we get a Z2, and now C with odd grading represents eta. So the key question, which my guess is the most important part of your question and the part that I have yet failed to answer, is why is this eta as opposed to some other element? And that's the key to this computation is like if you have a Picard 2 groupoid, so a symmetrical noidal 2 groupoid, such that all objects are invertible, there's a formula for the K invariance. Let me actually, yeah, so let me just, so there is a formula, oops, so. For the K invariance of a Picard 2 groupoid, due to, I believe, Gursky, Johnson, so Nick Gursky, Niles Johnson, Angelica Osorno. And I'm going to be honest, I do not remember whether there's a fourth author on this paper that I'm thinking of. They have some papers with just the 3 of them, some papers with other people. So if there's a person I'm missing on this, I'm sorry. So so to give you a sense for why is it actually, you know what? I do not remember the formula offhand. So if I try it now, I'm worried I'm going to mess it up. But you can use this formula to compute the K invariance. And ultimately, it comes down to the fact that there's the Koszul sign rule on the tensor product. If you take 2 odd elements and tensor them together, the order matters by a minus sign. And that is the thing that leads to a non-trivial K invariant between pi 1 and pi 2. And then you can do something else to get the non-trivial K invariant between pi 0 and pi 1. So somehow it's that Koszul sign rule that's making everything work. I hope this was what you had in mind with this question. If there's more I can say, please let me know.
Actually, it kind of was. I mean, I'm not saying that I understand all of it, but yes, thanks.
Oh, okay. Cool. If there's more that I can say about this now or afterwards, please just let me know. Any other questions? Okay, so going on, If I take an E infinity ring spectrum and I take a Postnikov quotient, so kill everything higher than degree 2 in this example, then that is an E infinity ring spectrum. And the way I always thought about it is I'm taking a ring and I'm quotienting by the ideal of things in high grading. But that's very, very far from a theorem. So, let me maybe not say more about the actual proof. But the upshot is that the dual of supercohomology is an E infinity ring spectrum. So we have the abelian infinity group of units. So a group like E infinity space. And so we may consider twists of this thing, and therefore twists of supercohomology. Um, Fortunately, this thing is pretty easy to understand. I'm going to focus on the classifying space because that's what classifies twists. So what do we got? We got KZ21, KZ22, KZ23. Now I need to say something about this. The first is this is not an equivalence of E1 spaces. So in other words, it's an equivalent. It's sort of like saying I have an equivalence of sets, but it's really not an equivalence even of groups. And these are both E infinity spaces. So like that's somehow even especially bad. So that's the bad news. The good news is for the applications that we have in mind with twisted supercohomology, this is we don't need to worry about the E infinity structure here. And if you do need to know the E infinity structure, it's known. Basically, you postulate there's the only K invariant that can be connecting KZ21 and KZ22, and KZ23 still splits off. Now, these three pieces are pretty different. So this is so the degree 2 part is the same as the degree 2 twist for KO. And so this is the focus today. The degree 1 part just as tractable. So in applications, the degree 1 part doesn't come up as much, but that's fine. So we're just not going to worry about it today. But if you need to do a computation of that, the same methods work. But this KZ23 is very mysterious to me. Which is to say, I know where it comes from in the sense that I know the proof of this lemma. But in terms of actually seeing this concretely in terms of the application to mathematical physics or doing any computations with a non-trivial degree 3 twist, this is something I would love to know more about. And so I have some, if this is something you're interested in, I'd be happy to chat about it. I have a little bit of sort of vague rambling speculation, but ultimately that's just a big old question mark. So given a space X and a class B in H2 of X with mod 2 coefficients, the twisted supercohomology is defined to be the Homs from this thing. And I need to say what MB is. So this is the Tom spectrum in the sense of Ando, Blumberg, Gepner, Hopkins, Resch of the map X to KZ2 to BGL1 tau less than or equal to 2s. So B being a cohomology class gives us a map to the Eilenberg-MacLane space, and then from the decomposition above, which even though it's not an E infinity or an E1 equivalence, it's still canonical. So we can do this and get a twist of supercohomology. And our goal is to compute, say, star of XB, where X is BG for groups of interest. which is to say other computations of supercohomology are surely interesting, but this is the thing that I'm most interested in. And then especially in low degrees. One of the one of one of the great blessings of working with physicists is that they don't really care about anything that happens above dimension 11. And this means there's a large number of things that mostly we can't do in homotopy theory because they don't, they're not considered because they don't work so well in arbitrary degrees. But if it gets you past degree 11, you're good, you can do it. So that's a thing that I do like. And so we're going to focus on low degrees. One comment is this whole question is trivial away from the prime 2. And the reason is, if you look at supercohomology, if you localize it any odd prime, the 2z2s coming from eta and eta squared go away. And so you're just left with ordinary cohomology. And this twist untwists, so kz22 also is trivial over an odd prime. So for this reason, we've been pretty much exclusively focusing on p groups, or sorry, 2 groups, because otherwise the story is literally just ordinary homology or cohomology. So let me give you the heuristic version of the main theorem, because time's passing faster than I thought. So let me say this: the hastened atom spectral sequence, which I'm going to call the HASS or HAS. Oops, sorry. So let's see. So first we've got Behrens, Hill, Hopkins, and Mahowald, and Bruno Rognes, who wrote this really nice systematic account. So the theorem is this can be applied to this truncation and some other spectra of interest. Which I'll say more about. And as a result, there is a strongly converging Adams type spectral sequence computing this twisted dual of supercohomology. And because we're looking at, if you're looking at a finite type space, this is equivalent data. So it's trivial to pass between this and supercohomology. And then, I mean, it's an Adam spectral sequence, so it computes the 2 completion, but as noted above, that's all the information we need. And the most important part is that this is tractable in examples. So that, calling that as part of a theorem is sort of a, not really a mathematically precise statement, but there is a precise statement that it had some of the differentials which would come up in the ordinary Adam spectral sequence for this go away. You don't, and so in that precise sense, it is easier in general. Okay. So when I say tractable, it's comparable to atoms for the KO homology of X twisted by B, which, thanks to the A1 trick, is pretty reasonable. Okay. More questions now or comments? So, for reasons of time, I'm going to try and go a little faster in this section. because, well, I wanted to say something about like this spectrum is not the most interesting spectrum on its own intrinsic accord. Like, okay, it's got three homotopy groups. Collectively as a field, we have some pretty powerful techniques. But I wanted to say something about like why the spectrum? What are we interested in? So the goal is to classify topological field theories. So TFTs. And if you've heard someone say topological quantum field theory, I mean exactly the same thing as they do. There's just, if you really want to be precise, being quantum is not a mathematical property of topological field theories in the sense I'm about to define. So it's like, well, this thing encompasses things that may be quantum, things that may not be quantum. It's sort of harder to make precise than the definition that we have. So so we have a Bordism category and some symmetric monoidal target. So a topological field theory is a symmetric monoidal functor from this category of Bordisms to something, which is usually complex vector spaces with tensor product. So what is the Bordism category? Closed n-1 manifolds are the objects, and then the morphisms, here's M, here's N, well, they're Bordisms from M to N. So, okay, really they're like diffeomorphism equivalence classes of Bordisms. And there's a lot of variants of this definition, for example, adding higher category theory, putting extra structure on the Bordisms, varying the codomain from vector spaces. And I'm not going to get into that. But to point out that if you want to classify, you got to specify you got to specify all that data. So an example is that 2D oriented TFTs, so your manifolds and Bordisms are oriented, are equivalent to the data of a semi-simple Frobenius algebra. So this is an algebra, and it also has a trace map, and there's some compatibility conditions or data. So that's not the kind of theorem that I'm interested in right now. I'm interested in, so the idea is what are all these semi-simple Frobenius algebras? And so there is a theorem that classifies these. And essentially it turns out, okay, it's a direct sum of simples. What are simple algebras over the complex numbers? Well, there's not so many of those. And so you have the complex numbers as an algebra, and then you have a trace on the complex numbers. And so you've sort of taken your topological field theory, and you've really chopped it up into this very straightforward data. So that's the kind of thing, is like instead of saying, oh, it's the blah, blah, blah algebraic structure, we're going to say, how do I classify the algebraic structures? So in 4D, now 4 dimensions is a lot of dimensions in topology. And so it turns out that this question is very hard. So conjecturally, it's classified by the data of a fusion 2 category. So this is due to Chris Douglas and David Reuter. And so what is a fusion 2 category? Well, it's a complex linear, so enriched over complex vector spaces. And I think we need one more condition about some functors being linear. So complex linear, semi-simple, monoidal, 2 category, such that all objects have duals. And now we need a finiteness condition. There's finitely many isomorphism classes of simple objects, and 1, the unit, is simple. So in far more common is the notion of a fusion 1 category, which is all over in 3D topological field theory. And so this is that, but you stuck the word 2 in front of everything and check very carefully that everything all makes sense. So as an example, there's a category of G-graded two vector spaces. And these are these are C-linear categories, which are isomorphic to the sum of n copies of complex vector spaces in some direct sum construction. You can also twist this. So this thing, by virtue of being a monoidal two category, has a pentaginator. So the thing which witnesses the pentagon identity. And the pentaginator has it's going to end up having four group elements in it. So you can twist it by a 4 cocycle. Okay. So the theorem, which is astounding, it's really a classification theorem. So lots of people. And this is just from, I forget, I think it was earlier this year, but it may have been 24. So fusion 2 categories are classified by not very much data. So there's a fusion 1 category, which I'm not going to say much more about, a group, finite group H acting on C, an inclusion H into G of finite groups, and a class B in H2 of BG, Z2, and a class in the twisted supercohomology of G. So somehow it's like we have a group acting on this fusion category. We want to extend the action, but there's going to be some sort of obstruction. Sorry, that obstruction is down here. So I realize I'm being vague and I'm sorry. So the takeaway is, let's say that we want to understand examples of fusion 2 categories. Which is a pretty reasonable thing. So in the fusion 1 category literature, there's classifications of fusion 1 categories that are small, meaning up to a fixed number of simple objects. And these tell us interesting examples that have shown up all the way in in condensed matter physics and quantum computation and representation theory. So it'd be great to have more examples of fusion 2 categories than we do. We currently only have a few examples beyond the ones I mentioned. So I would like to have more. The field would like to have more. So we got to compute twisted supercohomology. Okay. So I realize I only have about 5 more minutes. Maybe let me go. Let me quickly summarize the three techniques and what's wrong with them, or what's wrong with the first two and what's better about the second, and then I can state the main theorem precisely. Does that sound like that should fit in this time or 1 minute over? Does that sound good to people? Okay, I see a thumbs up. Great. So most computations already in this field are Atiyah Herzebruck. Like at this point, you can open up physics papers written by physicists for physicists and see somewhat technical Atiyah Herzebruck computations. So this is a standard thing. You filter supercohomology by the Postnikov filtration, and so you get a spectral sequence with just 3 rows. And so what can we say about it? It's less technical. which is really important in an interdisciplinary field. The atom stuff that we're doing asks more of our readers, and that's something that honestly is not ideal. There's only 3 differentials, and 2 are easy, which is to say that they have a formula coming by the K invariant. And then there's the D3 given by a secondary cohomology operation, which is a little harder. But extension questions on E infinity are frequent and messy. So as an example, SH3 of BZ2, let's say reduced just to make it easier, and untwisted. This is a thing which, this has a difficult extension question already, although it's going to be isomorphic to Z mod 8. And so that's reported as 3 Z2s that are difficult to piece together. Okay. The atom spectral sequence. So usually, let's simplify things by using the atom spectral sequence is not one of those sentences that people say. But there's this remarkable fact that the atom spectral sequence for KO modules is actually really, really tractable compared to general, which is to say, I can work it out by hand, whereas if I tried a more general one, I would be truly stuck. So I know there's a lot of people here who are very good at more general atom spectral sequences. So I'm not trying to, when I say tractable, I mean really for me. So because supercohomology is a KO module, then we can really use that simplification. So take the unit map from S to KO, and you get an equivalence because this map is 2 connected. So we could have used this the whole time. So you get the KO module atom spectral sequence. So I believe Baker and Lazarev were the first to write down R module atom spectral sequences. And so the point is that E2 is X'd over A1. So just this, the subalgebra of the steering algebra generated by square 1 and square 2, which is really makes it possible to do things by hand. And then you have to modify what the cohomology is. So what we need is tau less than or equal to KO, smash over KO, the Thom spectrum of XB in KO modules. I hope that's the correct number of parentheses. And so this is usually tractable. And differentials can be hard, but there are much nicer extension questions on E infinity. And the reason is that multiplication by 2 is detected by H0. So the H0 action on E infinity tells you a lot of these 2 extensions. However, for twisted supercohomology, or strictly speaking, the dual, this is messier. There's always differentials. So I'm going to try and finish up the next minute, and I'm sorry. So here it is for, I'm going to show you for tau less than or equal to KO of a point to show you what the problem is. So you're going to have, this looks familiar, maybe the ordinary atoms for KO of a point. But then you have this extra stuff here. And you have these D3s. So if you want to do supercohomology in general, these D3s are going to mix with whatever differentials you have. And that's going to cause some problems because now you have these D3s, you have whatever else you have, and they mix together in complicated ways. So not ideal. And this is a problem for any atom spectral sequence which does not collapse. So BZ2 to the n greater than 1, dihedral group, symmetric group, quaternion group. So any computation you might want to make, you now have to face this problem. So to fix, use the hastened atom spectral sequence. So I'm going to say this quickly. And the idea is that we have a cofiber sequence. So in this one, it's tau greater than or equal to 3 ko to tau less than or equal to 2 ko, such that F has high Adams filtration. Here, F has filtration 3, which is good. High means bigger than 2. You can combine the Adams resolutions of tau greater than or equal to 3 ko and of ko into a better Adams resolution for tau less than or equal to 2 ko, essentially promoting D3 to a D1. Now, that doesn't sound so good unless, usually when someone says D3 is becoming D1, unless they're talking about athletics, they're not super excited. But the other thing is, there is an algebraic formula for E2, which is essentially so essentially there's a long exact sequence in X associated to the action of F on X. So this is a purely algebraic thing. And then the third term, the cofiber in that long exact sequence is the E2 page. So that's something which is tractable. And but here you need there need to be some technical conditions. So let me finish with our precise version of the main theorem. And I'm very sorry for going over time. The technical conditions mentioned by, that are delineated by Behrens, Hill, Hopkins, Moholwald, and Bruner Rognus. So maybe let me not. They are met for any Postnikov truncation of Ko and any Postnikov truncation of Ku. So we get, so we get the hastened atom spectral sequence, computing I star tau less than or equal to nko wedge over kom for any ko module, which I should say finite type, and then same for ku. And as I mentioned, it's strongly convergent and it's tractable in practice in that you can calculate the E2 page, and in general it's about as hard as the corresponding ko module atom spectral sequence. So I'm sorry for running over time. That's what I've got for now. The proof of this, the proof of this, it's true for a kind of curious reason that I want to know more about, but I'll leave that for later. So thank you all for your time. I'm sorry for going over. Please let me know if you have any questions.